Good morning. Welcome to Krishna's classroom. We continue from where we left last time. In fact, I was about to consider the consequences of the theorem that I have printed on the board now, and some computer update or software update came in, and the connection was disconnected. The connection got disconnected. Actually, the connectivity was not. So I had to abandon at that stage. But however, I think I did it up to a particular stage, giving the proof of this theorem. Now let us examine this theorem. Now we are going to look at the application of this theorem. This theorem says the following. You have a measurable space X. Measurable space X means X with a class of or a sigma algebra of measurable sets. Sigma algebra of sets which you call measurable sets. Now, what we assert is the following. See, you have two real measurable functions, namely u and p. Okay, from which we construct a or from which we construct a composition map from X to Y. So what we have is the following. We have u and v real measurable functions on a measurable space X. Now what we have defined is the following. See, phi is a map from R2 to Y. Which is assumed to be continuous. Continuous, because you can talk about continuity there, because Y has a topology on it, and we are working in a topological space, and R2 has the standard topology, and phi is continuous with respect to these topologies. Then what we assert is this. Phi composition F. Phi composition F from X to Y is we have assumed both u and v are real valued functions which are. So how do we we have already looked at the proof of this, and therefore I am not going into that. So the situation, I'll just put it in the graphically. This is what you have. See, X is mapped to point Ux the ordered pair Ux. So they are real valued functions which are measurable. This is to R2, the plane. Now you have Y here, and then you have the map Y taking it over to what is called phi of ux which we designated by x. Our claim is that h is a measurable. I just briefly outline the proof. This is already continuous. See, this is a topological space. This is also a topological space. So you have a continuous map phi from R2 to Y, and you have a map which is designated as f equal to 2v. Okay, so that defines a map from X to R2. And now what we proved was this. Both u and v are measurable functions. Then f is a measurable function from X to R2. Therefore, this is a measurable function, and you look at the okay, H. Yes. But what is this? This is actually phi composition here of phi composition f is a continuous map. This is a measurable function. Therefore, their composition is a measurable function. So what we proved was, in fact, what we have is these two real valued functions are measurable, from which you have to show that f is measurable. So that is what the proof that. Okay, so I am not going back to that, so you can look at that. That is just to reconnect whatever has happened the other day. Now we are going to, you see, this is a very useful theorem. It's a serving the purpose of proving several results related to this. Okay, or what you call an omnibus result, which serves you to prove various results. We will give some examples. The first result is this. U, V are real measurable on a measurable space X. And this implies, suppose you construct a map F which is equal to U plus IV. That is, the image is now in the complex plane. Then so F is now a map, F is a map defined from X to C. We are asserting that this is measurable. Okay, so how do we prove this? The proof is very simple. All that we need is we define Gx so G is a map from R2. Okay. Now, what you have is, so what happens is X gets mapped to Ux. This is in R2. Now, what we do next is map this to C. How do we do this? By simply taking U as the real part and IBX. So this is in C. And this map is what you call. Okay. So F is from, so this is G. This is the phi that you choose. Therefore, you have F is equal to phi composition G. Okay. You see that from R2 to C, the map phi xy equal to x plus iy is a continuous map. Now you know that u and v are real measurable functions. Therefore, the map G that you have, that we have defined, is a measurable function. So G is measurable, which is the one that we have proved in our last, in the proof of the main theorem that we have. Okay. Therefore, what you have a measurable function, you have a continuous function. Therefore, phi composition G, which is defined as F, is continuous. So that's the first application. The second application is the following. When these are all results that easily follow from these are the results which you would have to every now and then make use of in our analysis. So we put them all on the shelf. Prove them and keep them on the shelf so that we can use them as and when it is required. So let us see the next one. Next one is the following. F complex function. That means F is a map from X to C. Now C is a topological space. X is a given measurable space. Now what we assert is the following. Then three statements are there. U, V and mod F. That means the real part of the map F, the imaginary part of the map F, and the absolute value of the map F. They are all functions from X to R. Okay. Real values, measurable, so for a complex measurable function, its real part, imaginary part, and its absolute value, they all define real measurable functions. How do you prove this? I mean, it's very simple. In fact, you have to begin with the measurable space X, and then you have the complex plane X getting mapped to now there are three different phi's that we choose. So we will designate by phi x, phi x is from this is the complex plane. So you have plus I. Okay. Phi x equal to u plus iv okay, that means phi x is a map from okay, so we write phi x of u plus iv okay. Now the map that we are talking about is this. So you take the map. So this is the map F. So you take phi x composition F is a map from X to, and this is essentially the real part map. Okay. This is essentially namely 2x x getting map so if I call this G, let me call this designate this by some name for this. So the U map is now a real measurable map or measurable function phi plus f that you have or phi x that we have defined is a continuous map. So this is from gets mapped so this is how. That's the composition. Similarly, you have the other maps. What are the maps? You see, the crucial part here is that the projection of C to the real axis is essentially a continuous function. So that's what we have used. So we have used the projection map. I think it's a better notation to better notation. So phi x is real axis along imaginary axis. and this is continuous. So phi x is continuous, f is already given as a measurable complex valued function, therefore their composition is this. Similarly, we define phi y as the projection in C to imaginary axis along the real axis. In fact, this is what is happening. This is the projection phi y. This is actually C. This is the real axis. This is the imaginary axis. So these two are now continuous maps, and then composing with f get you have phi y composition f maps x. It's a real valued function, and this is measurable because f is. So that is the second. Third part is this. Now we define the absolute value function. Okay, so we will define C to R what's it? Then again, phi is continuous. Now phi composition mod fx and this is phi is a continuous map. F is given to be a measurable function, therefore f measurable plus f mod f. So that completes the proof. Now we take up the next result, namely now we prove next result. This is rather big. Now the third assertion, giving some structural information. Namely, if f and g are two complex measurable functions, their sum is a complex measurable function and their product is also a complex measurable function. So let's write this. F comma g and x implies f plus g are complex measure. We first prove this for real. So we take the real case. The real case is this. Our assumption is that f and g are then f plus g is another real function real measurable. So this is the one that we prove and then use that to prove the complex case. Okay. So step. So how do we prove this? It's very simple. What you have is, again we take the Venn diagram, x, you have to actually take x gets mapped. F and g are two real measurable functions. So you have fx, give some name for this function, call this capital F. So we have fx equal to define and this is f from and you clearly see that this is a measurable function. Okay. Now what are we looking for? We are looking for the map from x to f plus g of x. So we take R. So take R and so this is the map f plus g. So we will call this map phi. So we write phi of f g. Now that's a map from R2 to R. Okay, and you know that this is continuous. Phi is continuous. Now you see that phi is continuous. Capital F is measurable from X to R2, which implies R defined by once again it's the application of the previous theorem. What you have is capital F is a measurable function, phi is a continuous function, therefore their composition is. Similarly, you have let me define let psi be from defined by psi of xy. Okay. Now take psi composition F, where F is the same as that we have constructed. We have defined above. That means F of therefore you see that psi is continuous and F is measurable. This we have proved at the beginning. That is, if these two are two real measurable functions, then this is a measurable function. I mean that we have. It's a measurable function from X to R. Measurable and is measurable. Being the composition of a continuous function and a measurable. Now we have proved the real case. Now let us see how we work on complex case. Complex case can be transformed into the real case. Then we work and use the previous theorem. And okay. So how do you do that? It's usual way of doing the following. Now you see what you have is, suppose measurable functions. Let the complex function f be written as f1 plus I f2, g written as g1 plus I g2, where are real values. Now you see that if f is a complex function, then its real part and the imaginary part are both measurable. If f is measurable, so f so also g measurable. Now you see you have f plus g is equal to f1 plus g1 plus I g2. So f1 and g1 measurable means f1 plus g1 is measurable. Okay, so f1 you use the previous part. f2 plus g2 is real measurable. Then by one of the previous results we have, what is it? Then you have f plus g given above is a complex a similar proof you can advance for fg also. Anyway, having written so much, let us completely write it up. So what we have is likewise f1 g1 minus f2 g2 plus I times f1 g2 plus f2 g1. Now f1 g1 f2 g2 are real measurable functions. Now f1 f2 g1 g2 real measurable implies that follows from the fact that the real part of a complex function and the imaginary part of a complex function are, if the original function is measurable, is complex measurable, then the real and imaginary part are real measurable. that is the product uh, rule, the product formula, which further implies that is complex function. So we make use of the real version of this result and use that to prove the result for the complex case. That completes it. Now, next assertion is that E containing X then the characteristic function of find as 1 x belong to this can be directly verified because you see the open sets are of 4 types. 1 containing both 0 and 2, containing 0 but not 1. And the third class is the following. Third class is the one that contains 1 but not 0. Contains not 0. Neither 1 nor okay. containing 0 but not put 0 element. So suppose B is an open subset of type 1. Then equal to polar. Suppose it is of type 2, then type 2 contains 0 but not 1. Now these are all measurable sets. So X, E complement are measurable. Which implies chi inverse perhaps open sets are two measurable sets. That is chi inverse is measurable. That means chi inverse chi is measurable. In fact, one can for one part we have already. If E is measurable, so now suppose not measurable, then B is of type 3, then by definition of measurability, so that concludes the proof that chi is measurable if and only if E is measurable. Okay. So we take up another consequence, which is these are all gives a representation, nice representation, real for complex value measure. So let us let complex measurable. Then there exists a complex measurable function alpha on X such that mod alpha equal to 1 and so to prove this, let us take the proof is let that is the points where F vanishes. Okay, so we take first of all this set is measurable. E is measurable. Okay, so we'll write this as one E component. Now we make an observation. Make an observation that f of x can be written as plus chi E of this is equal to, because we want to invert it on the whole space, and that is not possible because at places where it is 0 it will give you trouble. F is not invertible. So you have, if you analyze this, if x belongs to E, then you see that this is going to be equal to 1, but this is going to be 0. So this is 1 for x belonging to E, and this is equal to, on E complement Phi of x is 0 and the other one is fx. Therefore, this is now a non-zero function defined on the whole of x. Okay. So, second use of nice use of the theorem that we have put earlier. Is not equal to 0. It's a non-zero function. Now you define y as, that is the punctured complex plane. Okay, and you look at the following scenario. So we have x here, the punctured complex plane, where we have removed this we have removed, and this is 0. And then you have the complex plane. Now let us start from some x, and then you define, so gx you define as fx plus then g maps this to some point. So this is not so. It's in the complex plane with 0 deleted. Therefore, this is non-zero. G of x is a non-zero element. Now, what we do is g is not equal to 0. So we define now another map y z to be positive. What is that? It's a map from C/0, the punctured plane, to C. So let us define this by some point here. I mean, it is actually, you can see that this is on the unit circle. Okay. This is on the unit circle, somewhere on the unit circle. This is Z going to this is the map. Okay. Now what we do is for Z down into the punctured plane. Now you define alpha x as the opposition. Define as phi of now this is well defined. You can see that this is well defined. Okay, because this is not 0, therefore phi of this is well defined, which is the complex plane. So alpha maps x to see, in fact, to the unit circle. Okay. Now let us look at fx. Fx can now be written as alpha times mod f. Why? Because alpha is what? Alpha is given by now when x belongs to E, then fx equal to 0 when x does not belong to E, then fx equal to see it is gx divided by mod g. But what is this? If x belongs to E, this is equal to fx divided by mod times mod. This is not equal to 0, therefore this is equal to, okay. This is equal to what you call alpha x so that completes the proof. Okay, that's a nice result. I think I'll just wind up today here and then take it up later. Okay. So, thank you very much.